Well, it looks like everybody's coming on. It's not a whole lot more coming on right now. Maybe I should get started then?
Okay, yeah, go right ahead.
So welcome everybody to the latest in a series of webinars concerning the 2016 Summer Institute. My name is Rick Hooper. I'm the Executive Director of Quasi, and we're really excited about having this opportunity to offer the Summer Institute again at the National Water Center with the support of the National Weather Service. And so with this, today we're going to do a series of presentations, sort of lightning round talks, from students who were at last summer's Summer Institute or the National Flood Interoperability Experiment, the NFIE. And we have as our host today, Adnan Rajib from Purdue and Peirong Lin from UT Austin. Adnan and Peirong will be actually the course coordinators for this summer. And so if you're coming to the Institute, you get a chance to meet them again. And with that, I'd like to turn it over to Adnan and Peirong. And as I think Peirong has said, we're going to take all the questions at the end of the series of talks, and we'll go from there. So, Peirong?
Yeah, thank you.
Thank you, Dr. Hooper. Hello, everyone. This is Adnan. I'm a PhD candidate working with Dr. Venkatesh Marwade in civil engineering at Purdue. Last summer, I was part of NFIE as a resident scholar, and this time I'll be working as a student coordinator. So keeping in mind the growing interest from the scientific community and to let the new applicants know about NFIE activities, we wanted to feature some of the outstanding contributions from last year's program. And that is the sole purpose for today's webinar. We will be having 7 presentations today, divided into 4 major domains, such as model evaluation, river bathymetry, flood inundation mapping, and web services or software development. Next. First of all, let me talk about the motivation for NFIE in a very simplistic way, the way I saw it. This is important particularly to the new potential applicants for this year who are new to this concept. To give you some numbers, I took the example of Ohio River Basin. As you can see, the red dots on your screen are basically the USGS Streamflow gauge stations nested over the NEG Plus stream network. And my analysis showed there are 700 active USGS gauges having more than 15 years of continuous data. But the total drainage area for the entire Ohio basin is around 500,000 square kilometers, which means we have 1 gauge for each 700 square kilometers. Next. Obviously, just 1 gauge in approximately each 700 square kilometer is not sufficient to support an efficient flood emergency response. Whereas in reality, flood can occur at any time, at any place along these small blue lines, which we can see in the screen. So we have nearly 100,000 reaches in the Ohio basin, according to NEG Plus. And for the entire continental United States, the number is 2.7 million. So the question is, how can we generate near real-time information everywhere? And that's where NFIE came into picture. So we had a pretty intensive and very fruitful Summer Institute last year with 44 students coming from 19 universities gathered in the National Water Center, Tuscaloosa, Alabama. Next. Starting from June 1, 2015, the first couple of weeks was a boot camp where all the students were exposed to advanced lectures on modeling and skills related to flood modeling and emergency response. And the lecture sessions were conducted by some of the most prominent figures in hydrology, data science, atmospheric science, and GIS. We had people coming in from NCAR, US Army Corps, ESRI, National Weather Service, even Microsoft, and interesting with students to trigger their ideas. And the most interesting part in the boot camp was the multiple student-faculty brainstorming events that eventually led to formation of 18 different project ideas. Later on, in the next 4 weeks, the students executed their projects. Each group comprised of 3 to 5 students, and most amazingly, all of them from different institutes. That actually helped the students to build new collaborations, strong collaborations outside their own institute. In the final week of the Summer Institute, students presented their work in the Quasi Hydroinformatics Conference in the University of Alabama through lightning talks and posters, and it didn't end there. Students went back to their own institutes, continued working with their own advisors and the collaborators whom they met in the National Water Center, and finally submitted research papers in the Journal of American Water Resources Association. That's how the Summer Institute, more specifically the students, contributed in the advancement of NFIE concept towards the next big step, which is the Summer Institute for this year. Now, I'm going to hand over to Peirong Lin, who will be my colleague as one of the student coordinators this year. Peirong, why don't you go ahead and introduce the speakers?
Yeah, hi, this is Peirong Lin, and I'm currently a PhD candidate at UT Austin. So this year I will be working with Adnan Rajib to serve as the course coordinator for the 2016 Institute at the National Water Center. So today we have actually 7 out of the 18 groups that will be presenting their work. They will summarize what they initiated from last summer's work. So we have, I will be the first speaker to talk about hydrologic evaluation, and then Tim Lammer will, from University of Arizona, will be introducing his work on WRF-Hydro, and then Xin Zhen will be introducing from the hydraulic modeling work. Then Caleb and Sammy will be introducing their work on flood inundation mapping. And finally, Nathan, Swan, and Julio will be introducing their web service and software development. So I'll be the first one to introduce our work, which is on the spatial-temporal evaluation of the evapotranspiration and streamflow in the NFIE modeling framework. And this is also submitted to the JWRA featured collection, and this work incorporates my group members, Adnan. Also, Marcelo was then a postdoc at UT Austin, and Yan from Hohai University, China. So this is a slide extracted from what Dr. David Maidman's presentation from last webinar. So there is a national water model developed at the National Water Center. Essentially, the weather model and forecast 3-kilometer resolution forecast at 15 hours lead time is fed into the WRF-Hydro framework for landscape hydrology simulation, and then the runoff is being routed through the NHD Plus river network, as you can see from the blue lines here. That provides the 2.7 million river forecast at 2.7 million river reaches, and that augments the current flood modeling capability. So our motivation for the work is the national scale flood model forecasting system needs extensive performance evaluation. And in fact, last summer we focused on several important variables such as evapotranspiration, streamflow, and its individual components such as surface runoff and base flow. We try to understand the cause and effect relationship and trying to provide mechanistic understanding towards future model improvements and eventually to operational flood accuracy. We selected Texas as a testbed and did a 4-year simulation, including a wet year in 2008 and a drought year in 2011. So this slide shows the evapotranspiration comparison with the MODIS 8-day ET data. On the left figure, we show the percentage ET differences between model simulated ET and MODIS ET. And no matter it is in a wet year or in a drought year, or no matter which season it is seen that the model simulated ET has aridity dependence. For example, in humid region, the model is under predicting ET, but in arid western Texas, the model is over predicting. On the right side, we show the temporal correlation of model and observed ET values, and it is shown that in the wet, the ET is better predicted than in the drought year, which the drought year ET problem is probably related to the model problem with capturing the vegetation dieback. And we also compared ET fluxes with the FluxNet observation at Central Texas, and it's shown MODIS data better matches with the site observations. So in the next slide, we did a comprehensive streamflow evaluation against the 271 USGS gauge stations. Each dot here we show 4 statistics of the model comparison versus the observed data. correlation coefficient, Nash Sutcliffe efficiency, normalized RMSE, and normalized bias. It is shown that this is without any calibration. It is shown that the model is generally predicting very good streamflow in eastern Texas in humid regions, especially the regions surrounding Austin area. We have more than 0.7 Nash efficiency, but in the western Texas, the model shows a large positive bias, which resulted in a negative bias. This is also suggested by the hydrograph here. So in the next, last summer we were also interested, despite the total streamflow, we are also interested in evaluating each individual component. So there are lots of methods to evaluate surface runoff and base flow. One method is to use graphic method, and also isotopic method can be used to separate runoff. But the problem is how to evaluate model simulated runoff components separately at large scales. So last summer we came up with a way to run a recursive digital filter to 271 USGS gauge stations. And then we came up with this large-scale comparison between observed surface and base flow values versus the model predicted base flow and surface runoff value on the right side. It is shown that the first thing you can see that the highest NFIE values corresponds to those locations. The base flow and surface runoff are better, are very close to the observed values. But for we can see prominently in wet regions, the yellowish dots that the surface runoff over prediction problem in the wet region, and also in dry regions there are base flow over predictions, which is shown by also the yellowish dots as compared to the left orange dots. And in fact, the base flow over prediction results in a big problem in dry regions total Nash Sutcliffe efficiency, because that region does not have much runoff, and such 0.4 to 0.6 millimeter per day runoff bias results in the negative NFIE there. And this last slide shows we plotted the ET bias as the x-axis versus the runoff biases on the y-axis. And it is shown that the ET biases has a better one-on-one relationship with the subsurface runoff biases as shown by the right figures, whereas this relationship is less seen for the surface runoff. This is reasonable because ET is a very slow process which has more influence to the storage terms, such as the base flow, things like that. So this has implications for our model improvements. Calibrating ET against remote sensing data would help improving subsurface runoff simulations to improve the overall Nash Sutcliffe efficiency. So the summary of our study is that both streamflow and ET simulations have aridity dependence, and dry regions are actually more problematic than wet regions. And for flood forecasting, perhaps more focus should be focused on wet region ET calibration, which will eventually help with improving flood forecasting accuracy. So that is my presentation. So next, we will advance to the next speaker, Tim Lemma from University of Arizona. Tim?
Hi, Peirong.
Could you take over? Hi.
Yes, can you hear me?
Yes.
Okay. All right, so so my presentation deals with some of the work that I did with Mohammed El-Sadini. He was my partner during the 2015 NFIE Summer Institute for some work that we did with WRF-Hydro. And our other collaborators were Dave Gauchy and Fernando Salas, who helped us set up WRF-Hydro and Rajib throughout the process. So our WRF-Hydro configuration was basically, we tested two different configurations of WRF-Hydro. The one on the right is NFIE Hydro, which is similar to the one that was in your presentation, Peirong. And then the one on the left is the WRF-Hydro with full physics that included, of course, no MP land surface model, overland flow, channel routing, and base flow. And we used a diffusive wave routing channel routing scheme in place of Rajib for our WRF-Hydro full physics run. Again, our forcing precipitation for both runs was NCEP stage 4 for one set and NL-2 precipitation. All of the other variables, meteorological variables that were needed to force WRF-Hydro were from the NL-2 data set. And then using both configurations, we compared the model streamflow to USGS observed gauge streamflow. Next. Okay, thank you. So the WRF-Hydro configuration is kind of illustrated here. On the top left, you see a figure with NFIE-Hydro. With NFIE-Hydro, we use the NHD plus catchments and the NHD plus channels and catchments. And so all of the water that fell onto, that became runoff from the NOAA MP land surface model was aggregated by these NHD catchments and then directly put into the channel network. Whereas the WRF-Hydro, oh wait, back up, thank you. Whereas the WRF-Hydro channel routing scheme is a little bit more complex. The WRF-Hydro channel routing scheme had its own terrain routing grid, and so that all the water, base flow from the bucket model, surface runoff, and subsurface flow could go into the channel network. The WRF-Hydro domains that we used are shown on the right, and the dates we ran for NFIE were April 1st to October 1st, 2008, and then we extended that to 2014 in the JAWRA paper that we're still working on right now. Can you go to the next slide? So these are our results for the NFIE project. The NFIE-Hydro solution was generally more weakly correlated with USGS gauge data in lower order basins. And this is consistent with the streamflow time. I should point out that during the NFIE Summer Institute, we only tested WRF-Hydro during 2008, which was a relatively wet year. So correlation coefficients from NFIE-Hydro were relatively weak, and this is consistent with the streamflow time series being a little bit too flashy. The added physical processes in WRF-Hydro seem to alleviate this particular problem. If we go to the next slide, you can actually see the flashiness. So the flashiness in the green solution from NFIE-Hydro is sort of similar to the results that Peirong showed, particularly in arid basins. So for our some preliminary findings from our JAWRA paper show that the consistent negative bias of WRF-Hydro persisted in the years 2009 to 2014. That was also one of our key findings from the NFIE Summer Institute, was that even though WRF-Hydro clearly had added value over the for NFIE-Hydro, it was subject to some pretty substantial negative bias, and this seemed to persist even in other years. So it's likely that it wasn't a spin-up issue. And NFIE-Hydro eliminates NFIE-Hydro eliminated some of the negative bias, but again, it really had a difficult time resolving some of the physical processes, and overall it was too flashy. This is 2012, which is a relatively dry year, and you can see compared to the this is the 2012 warm season. You can see that NFIE-Hydro, which is the green, was generally too flashy, whereas WRF-Hydro, while it was produced a more physically consistent hydrologic response, it also tended to underestimate base flow and had a fairly significant low bias. So these are some of our preliminary findings. Can we go to the next? All right, that's my last slide. So some future work, given some of the limits of WRF-Hydro that we found, particularly some of the negative biases, future work is adjustment of the land surface model, including the routing grid, the groundwater bucket, and some of the channel parameters, and addition of a channel loss function to WRF-Hydro. Channel loss is an important issue in arid climates such as Arizona, where essentially channel loss or infiltration from channels is where water that should be routed that's routed through the channel infiltrates back into the land surface. That's currently not something that's resolved by WRF-Hydro, and that's something we need to fix to perform impacts assessment in the Southwest. That's another potential line of research for future work, doing impacts assessment in the Colorado basin. that's my presentation, and I can take questions after the other presentations at the end. Thank you.
All right, thanks, team. So maybe speakers, could you please mute your computer speakers? Okay. Our next speaker is Xing Zhen from UT Austin.
Hi, hello everyone. Can you hear me? Can you hear me?
Yes, you're fine.
Okay, so please go to the next slide. Okay. So in NFIE 1, we successfully realized the translation from the weather forecast in the sky to the flow forecast in a Weaver. Now our next step is to go from the forecast discharge to the forecast water level and inundation extent. A potential way to do that is by solving hydraulic models. A hydraulic model named Spring, developed by researchers from UT Austin and IBM, is able to solve the one-dimensional Savina equation for all the reaches in a large-scale network. To make this model work, besides the discharge information from the national water model, we need to know about the Weaver bathymetry, Weaver geometry details. So last summer, our team was trying to figure out a way to integrate Weaver geometry information from different sources and organize them in a uniform and efficient way. Next slide, please. So in hydraulic modeling process, the typical unit of organized Weaver geometry information is cross-section. So during our project, we pick up a Hackett watershed in Alabama and looked into several possible cross-section data sources. The first one is the existing Hackett models that local organizations built for different Weaver segments in this watershed. The second one is AutoRoll, which is a rapid flood inundation model developed by Army Corps of Engineers. The third one is a custom GIS tool developed by a group member in our team, which is able to extract cross-sections from DEM. So after we got cross-sections from these sources, we put them together into a single dataset, and then by linear referencing, we identify the locations of these cross-sections on NFIE flow lines. Next slide. So during our implementation process, we found several problems with the cross-section approach to organize Weaver geometry information. The first one is cross-section overlapping at the Weaver confluence. This kind of overlapping is not expected in hydraulic modeling process. The second problem is that the number of cross-sections we get from local hydraulic models is too much for our continental scale hydraulic model. Therefore, we need to figure out a more efficient way to describe Weaver geometric properties. A temporary solution we came up during the Summer Institute is to rescale all the cross-sections on one ray and take an average of their shape to get a simplified cross-section for each ray. But the results are not so promising. Next slide, please. So in a nutshell, for our next project in the summer, the biggest achievement is not coming up with an approach that works, but understanding why the classic cross-section approach can't be used for our continental scale modeling. Also, when we dig the problem, we figured out that the Weaver geometry information we need for hydraulic modeling is not the actual channel shapes, but the relationships between water depth and several hydraulic parameters such as cross-section area, wetted parameter, channel top width, and hydraulic radius. These findings from our NFIE project helped us modify our research direction later on. Instead of cutting cross-sections along the channel, we decided to slice the terrain along the stream profile in increments of elevation. In that way, we can calculate the water volume in the channel at different stage heights. Based on the volume series, we can obtain several tables showing the water depth and hydraulic properties relationships, which can be used in our stream simulation now. That's all I have for my presentation. Yeah.
All right, thanks, Xin. Before we move on to the next speaker, could we ask those of you who are not speaking now, could you please mute your phone because we are getting some echo here? So there is
I think the echo is coming from the person with the 817 number.
817
if that person could mute by hitting *6.
Yeah.
There we go. Thank you.
Okay. Yeah, great. Much better. Thank you. So our next speaker is Caleb Buchan from Utah State University. Caleb?
All right. Can everyone hear me?
Loud and clear.
All right. As Peirong said, my name is Caleb Boyan, and I'm a PhD student at Utah State University. The other members of our NFIE group were Cassandra Fagan from Texas, Nicole Sangwan from Purdue, and Curtis Ray from Brigham Young University. Next slide, please. The motivation for our work stemmed from the fact that currently the computational expense of running hydraulic models render them impractical for flood inundation forecasting at the continental or even regional scales. Depending on flow characteristics, one may have to couple 1D, 2D, or sometimes 3D models that use very small time steps. They also require detailed bathymetric data as well as information about the built infrastructure that mediate flow. Another big challenge is that often stability issues arise. Next slide, please. So our project objectives were, short of running a full-blown hydraulic model, we wanted to develop an approach to flood inundation delineation that was relatively more scalable. We also wanted to be able to prescribe uncertainty to our inundation forecast, leverage the large number of head-craft models that have been developed by many jurisdictions as part of FEMA's National Flood Insurance Program, leverage the runoff component from land surface models that are coupled to atmospheric models as part of numerical weather prediction systems, and finally disseminate the results using web mapping applications. Next slide, please. Now, a little background on the types of data sets that were provided during NFIE. Two runoff data sets, one from the NOAA's high-resolution rapid refresh model coupled with WRF-Hydro, and the other from the European Center for Medium-Range Forecasting data sets were made available. For our work, we used the land surface model runoff component from ECMWF's integrated forecasting system. This output included a 51-member ensemble forecast that were produced with a 15-day lead time. Now, as some people have mentioned already, land surface models are typically run at a coarse resolution, making it difficult to use the outputs for local flood inundation delineations. For instance, the ECMW output is produced at a 0.1 degree grid resolution. So it's therefore necessary to downscale this data. And during NFIE, the approach used was to downscale the runoff by routing it through the NHD plus river network using the RAPID model, which solves the Muskingum equations efficiently over large river networks. Next slide, please. With this background in mind, the approach we settled on for our work was to run a series of steady-state head-craft models which used a range of flows as inflow boundary conditions. And then after that, we extracted rating curves at various cross-sections along the river into a library. With this rating curve library, we could then readily interpolate the stage at each cross-section and calculate the inundation depths as well as the extents given the streamflow forecast. Can you go back to the previous? This current slide shows the workflow for our approach. To streamline it, we created a tool we're calling RCAF to automate the approach. In the forecasting mode, the tool periodically checks a repository for newly available forecasts and calculates the stage and inundation. And then we triangulate the water surface elevation and then subtract the DEM from it to get the inundation depth. We also create an inundation probability raster where each pixel is a fraction of the ensemble members that predicts inundation. Next slide, please. We applied the tool to two creeks in Austin, Texas, the Shoal Creek and Onion Creek watersheds, and we tried to evaluate how the tool would perform by looking at the Memorial Day of floods that occurred in May last year. So on the left shows the progression of the flood through time at the section of the Shoal Creek, and then on the right shows the probability of inundation that we estimated. Next slide, please. In conclusion, the approach we came up with can serve as an intermediate step until the challenges with running hydraulic models are addressed. Since inundation on each reach is calculated independently, the computation can be parallelized to achieve good scaling. Outputs are produced in standard formats that can be served on web applications. There are, however, some limitations. The models from which the rating curves were developed are steady state and represent gradually varied flow conditions. Backwater conditions from downstream influences can cause looped rating curves where the same flow maps to different stages. Although weather inputs are a large source of uncertainty in hydrologic predictions, our treatment of uncertainty is by no means comprehensive. Now, if anyone wants to take up this effort, one idea is to apply it across different reaches and validate it and test it for scaling. Now, another idea that we had was to extend the rating curve to incorporate more variables other than flow, including like the hydraulic model parameters and different downstream boundary conditions. We also started a web mapping applications that we couldn't quite finish using the Tethys framework that someone's going to discuss later on. And then the code for the tools can be found on GitHub at those URLs. That's it. Thank you.
All right. Thank you, Caleb. Our next speaker is Sammy from UIUC. Sammy, are you there?
Hey, can you guys hear me?
Yes.
Oh, perfect. All right, thank you. Yeah, my name is Samuel Rivera. I work with Professor Barbara Minster at the University of Illinois at Urbana-Champaign. And my collaborator during the Summer Institute was Mark Gion Lopez from the University in Sweden, Uppsala. I think I'm pronouncing that correctly. But in any case, our project deals with using volunteer geographical information to create probabilistic flood maps. And next, thank you. Just to give you a little bit of the motivation, as we have seen, traditional flood inundation maps often require 1, 2, or even 3D hydrologic models or remote sensing data. And often, a lot of this data is limited by the spatio-temporal resolution of the input data. And so using it to provide real-time information about the flooding state, it's often challenging using these models. And especially for locations in which you don't have a model created or gauge data. And so at the same time, we saw that a lot of different outlets are disseminating a lot of flood information through either social media, news outlets, or emergency calls. And those information, those type of data have implicit information about the flood state and will tell you something about how the flood is disseminating throughout the region. And so the research objective of this project was really how can we extract the most amount of information from volunteer geographical information so that we can provide reliable probabilistic flood extent maps, especially in areas where you don't have a model or gauge data to calibrate it. And so this is sort of the conceptual overview. There's a lot of details that I'm not going to go through, but they put my email in the chat, so if you have questions after the presentation, you can email me your questions. But basically, we started by collecting, filtering. Go back, please, one slide. We started by collecting, filtering, and geotagging all the data points. And once we have the geolocation for all data points, we analyze whether they had photos or videos. And if they did, we used the pictorial content of those data to estimate floodwater depth in those locations. If they didn't, then we just assume a water depth and we input the location and the height of the water at that particular lat long into a probabilistic flood extent model, which then translated the probabilistic flood extent into the region around at that particular point. We worked in collaboration with Caleb and the other group. So we did a Shoal Creek case study during the NFIE Summer Institute, and in here we're presenting some of the preliminary results we got for the flood water depth estimation approach. As you can see, there's a social media video. In this case, it's a Twitter video. And from the 3D world in which we're reconstructing Google Streets, we can estimate then the flood depths by associating the level of the water in pictures. And so preliminary results suggest that the approach gives reliable estimates of floodwater depth in a few places in the Shoal Creek. In this case, I'm showing only 2 locations, or 2 points in 1 location, compared to the flood depths estimated by Caleb's group and his HEC-RES model. Next slide, please. So as I said, once you have a location and you have a water depth in that particular point, then the idea was, how can we use this information to translate it into flood extent? And so we developed this method that we're calling the Hydro Region Growing Algorithm. It complements image segmentation techniques with hydrological concepts to, from a single point with water depth, estimate the flood extent into the region. And so by doing that for all points using a Monte Carlo simulation, we get a probability of a single cell to be flooded given the number of simulations that predicted that particular cell to be flooded. And then after that, we just use a smoothing algorithm. In this case, it was a multivariate Gaussian algorithm to filter out the noise created by the high resolution DEM that we were using. Next slide, please. And so preliminary results of the approach for 2 locations in the Shoal Creek showed, potential of the approach to provide reliable estimations. One was for the downtown area in Austin. We compare our estimations with the HEC-RES estimation models done by Caleb's group, and we got an 85% overlap with their model. And you can see the BGI points in there are magenta and circles and triangles. And then the other location, we didn't have any model or gauge data, and so we had to validate it against FEMA maps, the 25 and 100-year flood maps. And once again, we had about 75 to 82% of overlaps with their maps. And so this project is still in its early stages. Mark and I have been working on it since we left NFIE, and there has been a lot of development, and we hope to apply this in another case study and submit this for publication at the end of the summer. But as I said, if you have questions or ideas, please shoot me an email. Thanks.
Thank you, Sammy. All right, our next speaker is Nathan Swan from BYU. Nathan? Hi, Nathan. Are you there?
Sorry, I was muted. Thank you. So what I'm going to talk to you about today is Tethys platform, which is an open source project that is the result of a National Science Foundation project, and how we used it in NFIE last year. So go ahead and go to the next slide. So our work, this was done at Brigham Young University. Our goal was to try and simplify or streamline the process of creating web applications for water resources applications. And Tethys platform was born out of that. It is a kind of scriptable approach, so it's not really a drag and drop, create your application using a graphical user interface. You use Python to build these web applications. Go ahead and go to the next slide, please. And so the Python SDK, or software development kit, that comes with Tethys provides a lot of convenience operations that help you work with spatial data, help you display it on maps, plot it, and kind of pull all these things together in a structured way. Next slide, please. Caleb kind of referred to this in his presentation. They started developing a web application as part of their NFIE project that was called First Responder, that would display some of the flood inundation maps that they were working with. Go ahead and go to the next slide, please. We also, as part of NFIE, extended the capabilities of a web application we've been working on at BYU called the Streamflow prediction tool. And this tool makes use of a different data set, the European Center for Medium Range Forecasting's runoff data set, to basically provide streamflow predictions on any reach of the NHD in the United States. It's a very powerful tool. It's got a pretty intuitive interface. You can click on the stream reaches. If you look closely, you can see one of those is highlighted, and it will show you a probabilistic forecast 2 weeks into the future on that reach. We also worked into it some a 30-year interim data set so that we could generate the return periods, which you're seeing on the plot there, and then we can throw up warning symbols, which are hard to see in this image, but there's little triangles of different colors to show kind of the warning level. We extended this as part of NFIE to work with the name is escaping me, the model that we've been talking about, the NFIE-Hydro or whatever, and to work with those data sets. So those are just a couple of examples. Please go to the next slide. For more, if you're interested in using Tessa's platform for NFIE or any other project, you can visit the website tessasplatform.org, or get a copy of these slides. You can send me an email. And hopefully it will be a tool that can help delineate or disseminate some of the results of NFIE in an intuitive format. Thank you.
All right. Thank you, Nathan. So we will move on to our last speaker today, also on web service development. Ju, could you please take over?
Yeah, sure. Thank you, Peirong. Good afternoon, everyone. This is Zhu Liu, a PhD student from Purdue University. Other team members for last year's Summer Institute in our group includes Hongju Yu from University of Bangkok in South Korea and Tong Wan from University of Alabama. During National Flood Interoperability Experiment last year, our team developed ArcGIS-based tool to run this flood model. Next slide, please. Thanks. So let me first introduce the model a little bit. This flood FE is a raster-based hydraulic model that is used by the European Flood Alarm System to generate flood inundation estimates. The reason to do this project is because currently there exists no friendly GUI for this model, and thus it's difficult for people to prepare data, and it's very time-consuming and difficult, and conduct the simulations. So this work relates to the NFIE because it can take the advantage of the streamflow output from some other hydrological models like WRF-Hydro and RAPID, and use it to generate as the input for the hydraulic model to generate flood maps. So this tool is based on the C# coding environment, and the basic idea is that users can use the DM, streamline, and the upstream and downstream boundary conditions like the flow input and the water depths and the downstream to generate the input for this flood model, and also directly run the model inside ArcGIS. Next slide, please. Thank you. So firstly, the tool can create the cross sections for the streams based on the same spacing, and then it can generate extract the profiles for each cross sections by getting the information from the base DM, and then it can calculate the river geometries like river width, river depth, slope, and everything based on each cell. After that, it will create input files for this flood FP model based on the specific solver you select. For example, next slide, please. If you select diffusive solver, it will generate like 3 input files for the model. If you select the subgrid solvers, it will generate the corresponding 5 input files. And then it can run the this flood FP model directly inside the ArcGIS by using these input files. Next slide, please. Thank you. So this is one set of the preliminary results for the at the site of Elwha River near Elwha City. So the left panel shows the results from the diffusive solver, and the right side shows the results from subgrid solver by using these two. So basically, based on these results, basically we can calculate like F statistics and C statistics, those kind of parameters to based on some reference like observations from Landsat images, etc., to analyze the results. Next slide, please. So also, this tool can also be used to generate the animations based on the output from the lead lab. For same fixed time step. And here, because I didn't show the animation here, but I just show the results of each time step, but basically we can use it to generate animations. So that's all, thank you. So that's all what we have. And if you have questions about this, you can send me an email. So I will type my email at the chat box, and that's a lot for your attention.
All right, thank you, Drew. So we have finished all the students' presentations, and we will be taking questions. Is there any questions from the audience?
Yes, just type them into the chat box. That's the easiest way to ask a question. And I know a question I would have after listening to these presentations, which are all quite impressive. So if I were a student considering taking this class, what kind of background do I need? So how strong does my programming background have to be able to get something out of the class?
Adnan, do you want to answer this question?
You can go ahead regarding the WRF-Hydro sort of stuff.
Yeah, so definitely we think there will be any computing skills or programming skills will be very much desired for taking this application, but also we will be, like during this summer, we will also have this boot camp or 2 weeks training training courses. So as long as you have some basic knowledge about modeling and basic programming, I think it should be fine. It's just, and we also have 6 to 7 team leaders, faculty advisors who can advise us to do projects that we want to work on. So I think it should be fine. Yeah.
Okay, great. BYU has a question. Will students sign up for a project under one of the themes? How will they be assigned to this theme?
Adnan?
Okay.
Do you want to
so yeah, actually the students while they will apply this time, they will have an option to select probable themes, and the theme they will select actually it should be based on their experience and their background. So probably what we'll be doing this time, based on the students' response while they are based on their application, we will aggregate them into groups, and that's how it will be working probably.
Yeah. So on your application, you have the we want to sort of see what your interests are, and then, but there's going to be flexibility when we go through the boot camp, right, Adnan? That people will be able to select based upon their interests as projects emerge.
Yeah, definitely, and probably. Yeah, sorry. Go ahead.
Okay, I just want to say from our last year's background, we'll have 2 weeks long boot camp, and during that time, students and faculty advisors will have lots of interactions during that time. So you can basically shape your project ideas and shape your teams at that time. Yeah.
Any other questions? Okay, do students decide the projects or the faculty theme leaders?
Well, as Peirong just explained, like in the first week, there will be a lot of brainstormings and interaction with the faculty advisors, team leaders, and the student. So it will be a combination of both. Like your interest has to be within a particular theme, and within that particular theme, you can actually discuss with the advisor, with the faculty team leaders to find out a specific area. So it doesn't have to be like a very hard line that you have to do whatever you are asked to do. It should be interactive, and based on the interaction, based on those discussions, you will find out what you want to do.
Right.
Yes. I think regarding this question, I should also be advancing to this slide we prepared for. So you can, for anyone who are interested in the application, you can go to the Quasi website for previous webinars where the 6 theme leaders, they presented different themes. So the themes are pretty broad for now, so I think any students will be finding his or her own interest topic within the themes.
Yeah, I'll say one thing we're doing, looking a little differently this year too, is we hope to have funds to basically invite your advisor, your faculty advisor from your home institution, to come near the end of the boot camp period, because we feel like what will be very important is to engage your home advisor, home institution advisor in the process, so to make sure this effort kind of contributes to your overall thesis that you're working on. So we hope to be able to have the funds to be able to provide those additional resources to help that happen, which is different this year from last. And just a reminder, I guess it's 2 weeks from now is the deadline for the applications, and we encourage you to go to the Quasi website where there's more information there, and if you have questions, there's an email address there you can type your question into, or send anything to Emily Clark or to me, and we can try to address your questions. In this overall area, we're trying to keep this as flexible as possible. We also have to keep in mind that you need to be able to get something completed within the period of the Summer Institute. So it's kind of trying to scope the trying to scope the project appropriately so you can get something done. Caleb was asking, will this presentation be available online? Yes, it's being recorded and will be posted shortly after we're done here. Will be posted to the same website, the quasi.org/Summer Institute website. Okay, we are at, everybody did a good job of keeping on time. We'll give it a few more minutes if there's any other questions coming in. We hope that these presentations were sort of inspiring you and not too intimidating, I hope, but a lot of progress was made. Maybe Adnan and Peirong, you might want to be able to make a few comments on sort of just your experience, or the other presenters, your experience and how you felt, whether you felt that Summer Institute was useful for your research as a student and how it was part of your educational experiences. You might want to say that from your perspective as having gone through it last year.
Yeah, I just want to say a few words.
Yeah, sure.
I think it's pretty flexible for us. I feel very free during last summer to choose whatever I feel interested in to conduct my research, and also related to my dissertation work. And also, I feel like different backgrounds of students getting together is a very good idea, since I can learn different technical skills or different perspectives from different students, and this is a very good experience.
Yeah, I actually agree. That's because the most interesting part for me was to build different collaborations outside my institute. I continued working with Peirong even after I went back to Purdue after Summer Institute, and I'm still working with her. Again, at the same time, I built collaborations with some of the people from Army Corps of Engineers who were there during the boot camp, and I'm actually now working with them. So the NFIE is a framework where you go there and you build collaborations and you contribute to yourself and to the NFIE framework at the same time.
Great. That's a really important part of it. You can see it just from the presentations we heard today of sort of this range of institutions people are coming from, and it's a great opportunity to meet colleagues and form those collaborative partnerships. Well, I think that's it. We see nothing else coming in on the chat line, so I guess we will wrap it up for this session. So thank you very much, Adnan and Peirong, and to remind everybody that next week, on March 7th, Dave Gotchis, who's the main architect of the WRF-Hydro system, will be giving a presentation on WRF-Hydro. And Liz, you might want to be able to add to this. I believe that the registration is still open for the WRF-Hydro training class, which will be happening in May, I think, if I remember correctly. Liz, can you add to that? If Liz is on?
Maybe she has muted.
I think she may have.
Mm-hmm.
Sorry about that. Sorry. So early registration for WRF-Hydro is March 15th, and the final registration deadline is April 1st. So sign up if you're interested.
Okay, there's still space available then in the class.
Yep, there's plenty of space left.
Okay, great. And so Dave will be teaching that class in Boulder at NCAR. And what are the dates for that class, Liz?
It is May 2nd to the 4th.
Okay. So that's also on offer, and that's going to be very central then to the Summer Institute. We'll be using the WRF-Hydro framework. Okay, any last thoughts, Peirong or Adnan?
No.
Well, I just wanted to thank all the participants and especially the speakers. They put a tremendous job in such a short notice, and I know everyone is busy, and it was a great chance that they could show whatever they have done and their outstanding contributions. And regarding the participants, I hope to see many of you in the coming summer. So thanks for attending.
Right. Yeah. Thank you very much. Very good.
Thank you, everyone.
Bye-bye.
Thank you.
Thanks. Bye.
Bye.
Bye.